and welcome everybody. Um, so today is going to be a continuation of last week's introduction of Tapestri Insights. My colleague Yue provided a pretty good overview of how to go from loom files all the way to fish plots. Today, we're going to spend the bulk of the time into being able to select the right variants, the ones that are relevant for a disease model, as well as helping you, giving you guidance in terms of subclone selection. And so just as a reminder, this is the data set that we are going to be using. It is a 3 time point series from a patient that was sampled at diagnosis time point. That patient achieved remission at some point as determined by the clinician, and then unfortunately relapsed again. After applying the default filters, you'll notice that we are left with about 30,000 cells and 24 variants. As a reminder, the pipeline uses GATK together with a haplotype caller. So of those 24 variants, we do not expect to be all relevant for your specific disease model. And so this is really the mindset that you have to have in going into this task now to identify the relevant variants for your downstream analysis. The three key categories of variants that are listed in this table are either germline mutations of high quality that will always be picked up by our panels. Secondly are your somatic mutations that are pathogenic and disease relevant. And then a third small category are potential false positive variants that may have not been filtered out automatically by the filters, and you have to identify manually. And so this table on the top, you can expand. As you'll notice, each row represents a variant. On the left-hand side of this table, you'll have a collection of sort of qualitative metrics that are linked to annotations. They range from the function of a specific variant over to the protein change, including ClinVar annotations, as well as other metrics, including cosmic ID and allele the dbSNP IDs. So you have the function and the option, the flexibility to include or deselect columns as you go through this selection process. Something to keep in mind as well is all the annotations that you find in this table are based on the canonical transcript ID of a given variant. So if you have, for instance, a clinical report with a particular mutation, and that is being called at, for instance, at the IDH1 locus at 113, based on the HC19 build, and for some reason those annotations that are listed here don't make sense, feel free to just click on that little information icon, as it will allow you to click on the Learn More button, and it'll lead you to Varzome, which is the annotation database website that includes a number of different and additional information around this variant. So in addition to the qualitative metrics on the left-hand side, you see on the right-hand side, we have actually quantitative metrics that are directly related to the single cell data that you just collected. And so some of the key columns include the number of, or the fraction of cells that are genotyped for any given variant. And as you can see, that varies from variant to variant, because that fraction is dependent on a number of different things, including the sequencing reads that are available, the quality of the genotype, the amplicon on which that variant sits, etc. Out of those cells that are genotyped, we also have a column that allows you to display the fraction of cells that is actually mutated. By mutated, we mean either heterozygous or homozygous. We don't distinguish in this column at this point. And that's important for you to understand, because that will allow you to differentiate from potentially somatic mutations from potentially germline mutations that are universally mutant across all the cells and don't display any variants. So we'll come to that in a second. And since we loaded 3 different time points of one patient, you also have 3 supplementary columns that display the same data that we just saw in those 2 columns. So the fraction of cells that are genotyped and the fraction of cells that are mutated, only now on a per sample basis. And in addition, we have a metric that's called VAF by cell count and VAF by read count. We'll get to this in a second, but those are actually important metrics for you to understand in order to differentiate a potential high quality variant from a potential false quality variant. In addition, that by sample resolution allows you to first appreciate potential dynamic changes of any given mutation that might be part of your patient series. So we'll spend the first part of this seminar to walk you through some of the guidelines we have in place for you to help you make best sense of this table and how to go about variant selection. So one of the first things we recommend is actually using ClinVar as your first guide in order to sort your table when you click sort descending, in order to sort your table so that you bring all the variants to the top of the table that are associated to a ClinVar label. You see the minority of those variants does have a label, and then the rest does not have a label. The second column is the DAN score. And as a reminder from last week's series, the DAN score is a measure of pathogenicity. That's not something that Vision Bio computes, but that's something that is AI driven and was developed about 4 years ago. As you can see, after variants do not have a ClinVar annotation label anymore, variants are then sorted based on the DAN score. 1 indicating high pathogenicity and 0 indicating no pathogenicity. Once you've done that first step, you now can essentially go from top to bottom to select or not select a given variant because you want to include it for a disease model. Let's start with the first one, NRAS. It's apparently in the coding region. You see if you are a clinician or are in the heme space, you recognize that protein change. The pathogenic label is a key indicator that this is potentially a somatic mutation together with a DAN score of 1.00. It is genotyped in a relatively high fraction of cells, which is encouraging. And then this is one of the key metrics that now indicates that this is not a germline mutation, but actually it's a somatic mutation. Remember, anything that's between 0.1% and 90% roughly, or 95%, if you disregard high burden somatic mutations, are indicative of a somatic pathogenic variant. In addition to the 48% that are mutated, you can tell that those 48% are not equally distributed across your 3 time points, but rather you see this dynamic change of about 80% down to just 30 cells, so less than 1%. It rounds down here to 0%, and then up to 55% again. So we'll select that, because clearly that is something we want to include for our disease model. MPM1 is the next one. It is in the coding region. It doesn't have a DAN score, but it's important to note that no DAN score is not an exclusion criteria. It does come with a pathogenic label. In addition, it is genotyped in a relatively high number, not as high as NRAS. And this has to do with a number of factors, including this particular variant residing in a very GC-rich region. And we'll have a separate section on that actually in about 3 weeks, I believe, where we talk about potentially missing variants and how to go about retrieving them. And so the fraction of those 67% that is mutant is 65%, again, well within the territory of somatic mutant. And as you can see, again, similar to NRAS, you see this dynamic change from 91% down to less than 1%, up to about 91% again. So I'll select that. Moving forward to ASXL1, again, it now indicates it's a coding region, so it looks promising to be a somatic mutation. There is no ClinVar label. The only label that's provided is not provided. And the DAN score that's associated to that variant is relatively low. 0.31 is extremely low. Anything, to be honest, below 0.8, you can probably associate to a non-pathogenic variant. But let's say we wouldn't understand the DAN score at this point. The fraction of cells genotype, 97%, which is exceptional. And then this is one of the striking metrics now that leads you to believe that this is potentially a germline mutation. Every single cell out of those 28,532 carries the mutation as it's indicated here. As you can tell also across the samples, as expected with this metric, in each sample you have 100% cells mutated. And so this If I don't know, if I don't have any knowledge and this is a blinded analysis, I wouldn't include that for my downstream model. If you do select it, it's not going to harm or it's not going to change the interpretation of your ultimate disease model, because it's not going to change the clonal architecture. As you can see, it's invariant across all cells. But out of from experience, I will not include that. And DMT3A is the next one. This is a well-known variant within the heme space. It's pathogenic as indicated by the ClinVar database. It has the highest potential DAN score associated to it. And then again, the number of cells genotyped displays high quality, and the fraction of cells mutated is now 88%. Still, it's not germline character unless you assume high levels of dropout. So 88% on average. And in addition, you can see there is a small change across the board, 94%, 77%, and 92%. So I'll select that. IDH1 is the next one. High DAN score, highest possible DAN score. It is pathogenic. And then the fraction of cells mutated, again, nicely indicating that there is A, it's below 90%, and B, it varies across the board. And as you can tell, I make use of these changes across samples. So that's just another reminder that it helps a lot when you do have multiple samples available from one patient's patient set. So Tapestri Insights is specifically developed to utilize multiple samples from one patient to extract as much information as possible. Now let's go forward now. P53. As a potential variant that I want to include. It's intronic, so likely not. It's labeled as benign, as based on ClinVar, and it has a relatively poor or low DAN score. So all of these metrics indicate that's probably just a germline mutation. And that is corroborated by that metric again, 100% across the board. I'm not going to include it. EZH2, similar story. We have it's residing in an intronic region, again, based on the canonical transcript. It has a benign label, and it's in 97% of the cells mutated. So that, again, highly indicative of a potential germline, not including that one. EZH2 as well, you have the benefit of relying on this benign label, and the fraction of cells mutated, again, is 96%. So that's relatively straightforward. Now comes the set of variants that is linked to fewer information. And so it becomes a little bit more challenging to make the call of whether or not it's disease relevant or not. So RUNX1 as an example, supposedly it's in the coding region, again, based on the canonical transcript. We have a protein change label associated to it. There's no ClinVar annotation, and there is a pretty high DAN score. So all of this at this point suggests that this variant actually is disease relevant. When you look at the fraction of cells that are genotyped, it's also relatively high, around 80%. And then the 14% is right where you want a somatic mutation to be. 14% is exactly within that territory. Now, how do you differentiate that potential somatic mutation from a potential artifact? There are a number of different key factors. Number one, as you can see across the board, those 14% are relatively level across the board. So 15%, 15%, and about 12%. So if it is an artifact, you would assume it's sample independent and it's sort of systematically across the board, like 15, 15, 12. Another way now, and this is where the VAF by cell count and VAF by read count comes into place, is the ability to compare both metrics. And so I just want to remind you of what those metrics are. And so if you, I'm going to show that I'm just going to share that link in the chat box so that you guys can access that. So that's on our website on the support.missionbio.com knowledge base. Just a brief reminder why we have those two VAF counts available. So VAF by read count is really nothing more than your bulk sequencing. If you consider 3 cells, one of them being wild type, the other one being heterozygous, and the other one being homozygous as a specific variant, all we do is we strip all the barcodes from those cells. We don't care about cell identity anymore, and we total all the reads available. And so your VAF by read count is really your pseudo bulk, if you will. You simply divide the reads, the number of reads that carry the mutation by the total number of reads. In this particular example, it would give you about 46.7% with that read distribution. The VAF by cell count, on the other hand, doesn't consider reads. However, it does consider alleles. So we sort of assign allele counts to a given cell. A cell that's wild type has 0 alleles that are mutant, therefore it has 0 mutant alleles. A cell that's called heterozygous mutant has 1 mutant allele, and a cell that's called homozygous mutant has 2 mutant alleles. And so the equation here is slightly different from the equation above, that we divide the number of mutant alleles by the number of total alleles. And so in that case, we sort of binarize this number, and we get 3 divided by 6, giving you 50%. So what you'll see is that this difference shouldn't be discrepant. If it is discrepant, it either means there's some systematic error or some artifact, or there is this potential copy number event happening, where you may have an amplification of a specific mutant allele, and then the read count metric would be higher. And so this is just a short introduction of why we have those two metrics. And as you can see now with rungs 1, this particular one, you see a discrepancy of almost 2x across the board. And so again, if you don't expect any copy number, this variant should not be included. But let's say we include it, but maybe because we don't really understand this VAF count now. UTF-1, similar story. High GAN score, it's purely genotype, so not that great. And this 30% of cells mutant suggests somatic character. As you can see now here, similar to rungs 1, the VAF by cell and VAF by read count are not perfect. And just as a guide, we like to keep the difference below 1.5x. So that's sort of a rule of thumb. If you don't expect copy number, those two metrics should not be more than 1.5x different. So let's just assume I select that, and I want to be less conservative with the variant selection at this point. And now the rest of the variants, I highly suggest that you just keep an eye on the mutated cells. You shouldn't spend too much time in going through those variants. As you become more and more experienced, you'll quickly notice that all of these are now, all of these variants are likely of somatic character. PTPN11, 100%. As you can see, the VAF by cell and read count suggests it's a heterozygous mutation. This is germinal mutation, germinal mutation. Those are all germinal mutations, and you can tell by the VAFs if it's a potential homozygous or heterozygous germinal mutation. Like this one, RAP31, is potentially a homozygous mutation based on the VAF. And so this completes your sort of task of selecting all the variants. Once you're done with that, I suggest to click on this little inverted triangle and to only select the variants that you, or only display the variants that you just selected, just to help you with the analysis going forward. So I'm clicking this the button, select variants. So now you just discard everything that you didn't select. I can minimize my window. And now you see at the bottom the clones that are the result of your selection process up here. As you can see, every time you add a variant, you are changing the display at the bottom. The reason why I included those potential false positives is because I want to emphasize the point why you should make use of those metrics that are listed here in the parentheses. As a reminder, each column here refers to a subclone that is now defined irrespective of your samples. And those subclones, C1, C2, are ordered from left to right based on the relative fraction across all samples. So the C1 clone is your largest clone because in total it makes up about 6.18%. And those percentages are taking into account also the missing data. So if it's called heterozygous, that number should not be less than 40 or more than 60%. If a clone is a variant is called in a given clone homozygous, it should not be less than 98%. We don't have one here. And if a variant is called wild type at a given clone, like here, it should not be more than really 2%, to be honest. If it's more than 2%, then this is a sort of a red flag. As you can see, UTF-1 here, all the wild type cells in those specific clones have average allele frequencies of 2%, which is a red flag. And also the clone that's supposedly heterozygous is just 27% on average. So that tells you the allele frequency in that one just suffers some sort of potential inability to amplify the mutant allele, and that might be because of sequencing artifacts or other PCR errors. So as a result, the initial call I made, I'm revising, and I'm going to deselect that. Rungs 1, you see similar story. Your head calls are way below your 40% threshold, and so that already tells me there are other metrics you can use, but that already tells me that this is not worth considering. So I'm going to deselect rungs 1. So that leaves me with those 4 high quality variants. I'm going to call them now. I'm going to call the clones based on the pattern that I see. Again, the clones are the result of 2 things: the co-occurrence pattern of the 4 mutations across all cells, and secondly, the zygosity changes. This seems to be DNMT3A seems to be a potential founder clone because it's single mutant for that variant. We have a triple mutant clone, DNMT3A, IDH1, and MPO1. We have a wild type clone. You will always, in most cases, I would say, always find a wild type clone, which is the beauty of the single cell approach, because you can discard it and it's not going to impact your calculations with respect to the population frequencies. And then we also have a double mutant clone, IDH1 and DNT3A. So this is the C6 and C7 clone. Now, this is a territory where you're getting into an area where you have to be careful in assessing the validity of the clone. Remember, we have this fraction that we call small subclones, and 45 means there are 45 different types of clones based on the pattern that we just bucket into one group that we don't think are accurate. Those are allele dropout clones. Those could be small clones that are maybe the result of mixing or doublets. So we don't want to display them here because they will lead you to wrong interpretation. And we have this threshold of 1%, which can be changed as well. And so this case here, C6 now, when I interrogate that, it looks identical to my first one, the first clone. The only change is really the zygosity state, that NPM1 is called homozygous. And so unless I truly believe that this is a homozygous mutant, which is, from an oncology perspective, highly unlikely that both alleles are being impacted, this homozygous call could also be the result of amplification of the mutant allele, where you dilute out your wild type allele and GATK just recognizes the mutant reads. Another biological explanation could be that you lost the wild type allele altogether, and so then all you're left with is the mutant allele, so something that's known as loss of heterozygosity. And then from a technical perspective, you could just simply fail to amplify the reference allele, the wild type allele, and so that will be an allele dropout. So because I don't expect that this NPM1 is implicated in the copy number, I'm going to call this for now NPM1 DO1, dropout 1. The one right next to it, from experience, I'm going to call this NPM1 DO2. The reason why I call it DO2 is because if you suspect allele dropout, by definition, it's a random event. So if you fail in a certain fraction to amplify the reference allele, you should also expect that you fail to amplify the other allele that carries the mutation. And then as a result, you would get that clone where you only have available the reference reads. And so one way really for you to now corroborate your hypotheses that these are true artifactual clones and need to be removed from your analysis is by using this third panel of this page, which is called variant viewer. And so to walk you through how you go about this is you click a specific variant that you want to display. In this case, we are specifically concerned about NPM1. I always suggest to click on this little wheel so that you have some of the options here listed. This is a pretty busy page. You see lots of violin plots. Each violin plot refers to a given clone. So we have, 1, 2, 3, 4, 5, 6, 7, 8, 9 clones, including the two sort of garbage clones, if you will. So, and because we have 3 samples, you have 3 times 9, so 27 violin plots. Number one is I only want to show the clones that I care about for this particular type of analysis. So obviously my 2 potential dropout clones. And then in addition, I need a reference clone. And the reference clone is the one that I suspect my dropout clone drops out from. And so that will be my quadruple clone because it's heterozygous, it's quadruple mutant in all 4 mutations. So now this looks a little cleaner. Because I only really care about data, I'm going to get rid of my remission data sample because you see there's not many cells. And so that just lets you really nicely now review the quality of that variant. What we see is on the y-axis allele frequency. So that's just, again, a confirmation of what you already saw on the table. We have our heterozygous clone, quadruple clone that's heterozygous, and we have our 2 dropout clones, homozygous mutant and homozygous reference. One way now that you can really take advantage of is changing the y-axis, going to quality. Quality is, again, a metric for you to assess genotype quality. And we have another, actually we have another, I'm going to add this to the chat window. There is a knowledge base article that really talks in detail about the advanced filters, and quality is one of the advanced filters. So it highlights exactly how the quality metric is calculated for those of you who are interested in. The key take home here is that you see a pattern, and any clone that you define should not be the function of quality, which is clearly the case here. You see our 2 in both samples, diagnosis and relapse. The quality of our quadruple mutant clone is very high, with the highest possible value of 100. And then when you evaluate the red line, which is your mean, I don't recommend using the green line, which is the median, which is resistant to outliers. When you review that, you can clearly see that they are substantially lower. There's no statistic at this point associated to it. That will come in a later version. But what's important is that you always make this comparison relative to your true clone. And so in both cases, clearly that's a red flag and indicates low quality. In addition to that, read depth. Now I'm only going to look at one sample at a time because read depth is really a function of the sample. It's based on sequencing depth, and that may change from sample to sample. And what you can tell is that, similarly to what the quality already suggests, that your high quality clone, on average, that cells in this clone have about, let's say, 80 reads, as opposed to the cells that are now part of the C6 and C7 clone that come back with about, I don't know, 45 reads. So roughly half, which again nicely corroborates your potential hypothesis that indeed you fail to amplify one of the alleles and therefore you end up with just half the reads. And so as a result, this simple analysis enables me to now be more confident that those are potential dropouts. They're slightly above that 1% threshold, and I need to get rid of them. You cannot discard them at this point, so that's why it's important that you label them accordingly. You can and you will discard them and disregard them in your final chapter of your analysis, which is really the review subclones page. So just as a reminder, you have different options to visualize your data. The stacked bar graph is just a nice way to look at the relative differences of your clones across different time points. What's important now on the left-hand side is that you deselect everything that you don't want to include in your data, because that will change this table. So it'll discard those cells, and then all the cells from left to right add up to 100%, and you get a very accurate picture of your clonal architecture. Because of the fact that you have multiple samples loaded, I always recommend making use of the fish plot, which you can expand here, because it really just shows the dynamic changes of your clones over time more dynamically. So again, I'm just deselecting the clones that I don't want to include and should be part of my report that I ultimately export. And so in the end of the day, you only end up with the 1, 2, 3, 4, 5 high quality clones that you detected to be relevant for your disease. One way, just a friendly reminder, if you want to change or customize that, you can do that by changing the colors here. If you have time points, let's say 30, a month after diagnosis, you have a remission time point, you can say 30, and maybe, a year after that, you then have the relapse sample. So that's, let's say 360 days. So that just tells you a little bit more accurately when those samples were collected. Another and concluding remark is the ability to now sort of try to reconstruct the phylogenetic relationships between those clones. As you can already tell, and I go back here to this page, as you already could tell from the subclone table, it nicely illustrates that this might be the founder clone, DNT3A, followed by the acquisition of an IDH1 mutation leading to the double mutant clone, which is then by itself followed by the acquisition of an NPM1 mutation that leads to the triple mutant clone. And then ultimately, you result in a quadruple mutant clone by the acquisition of an oncogenic RAS mutation. This hypothesis also is very much in line with the frequencies, because if you do suspect that DNT3A is your founder clone, you would assume it has the highest variant allele frequency or the highest fraction of cells that are mutated. And when you look at on the top table, indeed, DNT3A actually is mutated in 88% of the cells, followed by IDH1, followed by NPM1, followed by NRAS. And so knowing that, it's not yet automated, but knowing that you have now the ability to include that, incorporate that in your model. So I typically select a clone and order them based on the acquisition. So wild type first, followed by DNT3A, followed by IDH1 DNT3A, then followed by the triple mutant clone. Now you can, and this is a very simple model, you can now use the right and left arrows to sort of depict that model. In this case, it's a linear model, really. There's no branching. So it's a very basic model. So DNT3A is followed by DNT3A-IDH1, which is then followed by the triple mutant clone, which is then followed by the quadruple mutant clone. And so that just sort of changes the visuals of your fish plot slightly and incorporates that knowledge that helps you interpret the overall disease model. And then finally, feel free to either save the report as a PDF, or what most people do actually is save the image file itself, either as a PNG or as a PDF or SVG in high quality, so that you can customize that outside if you want to in Illustrator as well. With that, I am closing this webinar. Again, friendly reminder, in the subsequent weeks, we will talk more about advanced filters, as well as the ability to retrieve potential missing variants that you expect based on your clinical reports.
Robert, that was fantastic. A really nice explanation of how you pick your variants and how you know which ones are real and which ones you don't want to include. So thank you very much. We have a couple questions from attendees. So will you always see the homozygous and wild type clone if it's ADO?
That's a very good question. Not always, because it really depends on the overall makeup of your clones. In most cases, your pair that results in the wild type call, where you are unable to amplify the mutant allele, in most cases, that clone is part of an existing clone that you already have specified as true. For instance, this clone here could be very well a dropout of this clone as well, right? Where you just fail to amplify the mutant allele and you end up with NRAS wild type. But the fact that we don't deem that as a potential dropout is, number one, the fractions are very high, and number two, the counterpart, the homozygous clone at NRAS, is missing, and it's not above 1%. We feel more comfortable about this being actually two dropouts because again, the fractions are relatively comparable. But yeah, it's a very good question, and it is more challenging to identify one of the pairs. But again, we can help you with that on an ad hoc basis.
Great. I think in a similar line, why isn't there ADO in the quad clone?
So something maybe to point out, ADO, so though you will always have ADO, that's just a feature of single cell genomics, given the fact that you start with just 2 templates. Because we have a targeted approach is relatively small compared to whole genome amplification approaches. And so really the vast majority is below 1%. What you need in order to actually detect and quantify ADO is a variant that is heterozygous at a given loci. If you have a variant that's called homozygous and one of the alleles drops out, you wouldn't recognize that because the zygosity wouldn't change. And so therefore, this is your largest clone. Because every single variant is heterozygous, by definition, that cannot be a dropout, or a cell that's inside that clone can very likely be the result of a dropout, because you in fact are able to amplify both alleles that would generate your heterozygous mutant call. I hope that makes sense.
Yeah, no, it's really good explanation. So an ADO has to be wild type or homozygous, but not het.
Correct. Everything that's small and that has het may be the result of potential multiplets, but those are even rarer and less frequently to be above that 1% threshold.
Okay. Another question here. How many variants should you select in that long list that you started with?
That's another good question. So that is dependent on a number of factors, including the number of samples you loaded, including the panel that you actually used to generate the data, and including the disease that you are trying to understand. So the larger the panel, the more likely it is that your variant count is higher. If you work with melanoma samples, for instance, just biologically speaking, you expect more variants because patients are inflicted with a larger fraction of variants in comparison to heme malignancies, where you would only expect a handful of variants at a given time. And so this is, I think this is a patient series linked to an AML case where you would only expect about 4 to 5, maybe 6 variants at a given time. It's important to note that the more variants you select, the higher the fraction of your cells that you disregard because they exhibit incomplete data. And so that goes beyond the scope of today's discussion, but you have the ability to select as many variants as you want, but because of the fact that Tapestri Insights is built in a way to discard everything that's incomplete, you may end up with not enough cells that are informative for your downstream analysis. So we have other approaches for you to recommend to continue the analysis outside of Tapestri Insights by exporting the data and working with other tools.
Great. So again, Robert, this was truly wonderful. I think this is going to be really helpful for all of our customers. This video is great. Is there a guide also that sort of explains how you select variants?
That's also a very good question. At this point, there is not. We have a glossary on our knowledge base that illustrates some of the key features and what they mean. We are in the process of publishing a rather comprehensive document that can be used as a working guide. So the timeline of that is in about 1 to 2 weeks. It'll give exactly the information that I just walked through with additional recommendations that were not part of today's discussion.
Wow. Well, that'll be highly anticipated.
Yes.
All right. Well, with that, we'll conclude office hours for this week. Again, thank you so much, Robert, and we look forward to part 3 next week. Thank you for everyone who joined.
Thank you, Kelly. Thank you, everybody.